So unfortunately I got to rely on your notes a little bit because when we did this, maybe I shouldn't record here, 50.6 grams of the magnesium hydroxide. We did our limiting reagent calculation on Tuesday and we determined that that produced how much magnesium chloride? 82.53 grams of magnesium chloride. For those of us being extra astute, that's wrong because sig figs, that's a little bit better. Okay. So what we now have to go through and do is do that same type of calculation for the hydrochloric acid. Now remember, to do all of this we have to have a balanced equation, which I didn't balance yet, right? What do I need, just a 2? So we'll start with our 45 grams of hydrochloric acid, and I want to convert that into anything? What do I want to convert that into? End goal. What's our final goal? What do we want? Percent yield is where we're eventually getting to, but I need to compare, decide which one of those is limiting reactant. So I need to convert it into grams of magnesium chloride so that I'm in comparable units. So while I'm fleshing in the percent yield stuff that we're going to later do, what I want you to go ahead and do is that conversion in purple. Set that up. Okay. Get me the conversion to go from 45 grams of hydrochloric acid into grams of magnesium chloride. Okay. What we've got at the bottom now is kind of our percent yield. That was our ultimate goal. Okay. To get our percent yield, we need to take our actual divided by the theoretical. The theoretical must be calculated using limiting reagent calculations. We did the first part with our magnesium hydroxide on Tuesday, and what we're finalizing here is what our yield would be if we used hydrochloric acid. Again, our process, like our grams of hydrochloric acid, the same thing as magnesium chloride. No, so I need to do a conversion. Okay, within that conversion, what do I know needs to happen? Grams of hydrochloric acid must disappear, so it's got to be on the bottom. Can I convert the grams of hydrochloric acid to anything? What can I convert it to? Moles of hydrochloric acid. Okay. Where do I find that conversion factor? I can get that conversion factor from our periodic table, which I'm just going to abbreviate PT. And it comes in at 36.45, 1 mole. So interesting statement on the sig figs. We know we only want, or 3 sig figs is in our starting measured value. As far as the amount of sig figs we should carry through in each of our conversions. Theoretically, all I need are 3 because that doesn't limit the amount of sig figs. But ideally, we always add or try to have 1 extra just in case, so we can minimize kind of error through the experiment or through the calculation. Kind of, sort of? Okay. That is a rule of thumb. It's one of the reasons why I don't like sig figs, but it's neither here nor there, unfortunately. Are moles of hydrochloric acid the same thing as grams of magnesium chloride? So what do I need to do? I need to get rid of my moles of hydrochloric acid. What can I convert that to? I don't want a number yet. Okay. Moles of what? Magnesium chloride. Okay, and sorry, Simon, I'm actually going to ask you to not participate anymore. Siri, what did you suggest? You said to go into grams of hydrochloric or magnesium chloride? Yeah. Okay. Do we have that conversion factor, though? No. Okay. So you're jumping ahead, which is okay. You just have to recognize that you're jumping ahead. So where do we find the conversion factor between moles of hydrochloric acid and the moles of the magnesium chloride? No. We can find that information from our balanced equation. We take our coefficients from our balanced equation. We have 1 mole of magnesium chloride is 2 moles of hydrochloric acid, right? The unit we would now have would be moles of the magnesium chloride. Is that the same thing as grams of magnesium chloride?
No.
So what do I need?
Conversion.
Another conversion factor. Where moles of magnesium chloride needs to show up on the bottom. What should show up on the top, Siri? Are grams of magnesium chloride. Where do I find that conversion factor? Go to the periodic table. That's one I can't do in my head. But we take the mass of magnesium at 24.31. We would add that to the mass of chlorine, 35.45. And because we have a second chlorine, we do another one, 35.45. We're at 70 and 24, 90 something? 95? Okay, everybody's shouting slightly different numbers, but they all started with 9. So let's start with that. 95.21 grams is 1 mole. Chandler, I know what you're going to try, or you're trying to fix that. Don't worry about it. Trust me, it's a nightmare. Moles of magnesium chloride. Okay, so our moles of magnesium chloride cancel. We'd end up with our answer, and as far as our units, grams of magnesium chloride. We can now punch it all into the calculator, and what do we get for our final answer? Okay, Simon, now you can speak up because I know you've calculated it. 50.7? Oh. 58.7 grams of magnesium chloride. Okay. We now have to decide our limiting reagent. Our limiting reagent means we have to compare similar units. Okay. The ones we're comparing are now in our green box. Which is our limiting reagent? Or what is the most amount of magnesium chloride that we could make for this experiment? I see where your number is coming from, but I asked magnesium chloride. 58.7 grams of magnesium chloride is the most we could make because the 45 grams of hydrochloric acid limit our reaction. Which means, what have we just found? The theoretical yield. Our theoretical yield is this 58.7. Okay, because I've been yelling at you to do it, make sure you use your complete unit. We can now enter this into our calculation. We would take 60.0 grams of magnesium chloride and divide that by our theoretical yield of 58.7 grams of magnesium chloride. Everybody okay with that? What do you get as an answer? Sorry, I left out. I always forget to times by 100. Times by 100 equals 102.21%. Though officially sig figs, we really only need our 102. Questions about any of that? There's tons of work up there, lots of writing, a lot of it overlaps. But our final answer out of all of that work is that we get 102%. Anybody have an issue with that? What do you mean it doesn't make sense? Can't you get over 100% in a class? Yeah? Okay, why can't we get over 100% here? There's no extra credit. Law of conservation of mass says I can't get more than what I theoretically expected as my maximum. Okay? So what does the typical student then do at this point when the calculator spits out this answer?
Just brings it down to
Probably said, I must have entered it into the calculator wrong. It should actually be 58.7 divided by 60. And that's now under 100%, right? That answer then makes sense because it's lower than 100%. I enter that in as my final answer, which of course shows up as a possible multiple choice answer. And it is wrong. Because what did you do to calculate that? You took the theoretical over the actual. So what we have to recognize is we must follow what the formula says in this case. Our actual is always divided by our theoretical. And yes, this results in a number greater than 102%. And we may say there's no physical way that can happen because we are thinking in a chemistry lecture. And in a chemistry lecture, we are working with theory or an ideal environment. When we step out of the chemistry lecture, we step into the lab, and what happens in the lab? Everything goes out the window. In theory, we don't break any glassware. In theory, we hit the perfect pale pink in our titration every single time. Okay. That doesn't happen consistently. The reality of our environment says weird things happen. Okay. In this question, were you asked to explain the percent yield? No, you're just asked to report it. Okay. In a real environment, what would you be expected to do? Explain it. Okay, fair enough, because you guys suggested it. Explain the answer. I shouldn't have backed you two. I told you the answer. What do you hear, Siri? What's that? When we weighed the magnesium chloride, was it just magnesium chloride? No. There had to have been something else there. That's why the mass is higher than we possibly could have theoretically gotten. What could that mass have been? What else was produced in the course of the reaction? H2O, also known as? Water. Water. Okay. Is it particularly easy to remove water? Yes. We just throw our clothes into the washing machine, right? And the washing machine removes all the water. We take it out and we put on dry clothes, right?
That's the wrong.
So it's not easy then. We add water to it, and the water stays on it. How do we get the water off? We put it into the dryer, and what does the dryer do? Use massive amounts of heat and electricity. Where did we get the massive amounts of heat and electricity? Somebody had to generate that energy somewhere else and then ship us that energy through what? Through power lines. Well, where the hell do the power lines come from? Somebody had to build the power lines just so that we could get the heat and electricity, or the electricity to generate the heat at our dryer so that we could remove the water from our clothes. Was that really an easy process to get rid of the water? No, there's a lot of things that go into that. So when it comes back to our experiment, more than likely what happened? They didn't remove all the water, which meant when they weighed it at the end, that 60.0 grams is not just magnesium chloride, it's magnesium chloride and water. That extra mass is what we're weighing, and that's why we see 102%. Okay. Why present this question? Again, because most students will look at that number and say, I can't possibly have 102%. I must have entered it in the calculator wrong. I'm just going to do it the other way because that answer also shows up. You cannot do that. Okay. The formula for percent yield, so if you've got to memorize a formula, here's a formula you can memorize, is actual over theoretical. Do not swap it. Make sense? So I got a word and then a what?
I'm not understanding.
Which part?
So how come we didn't use the 82.5? Because if you do the percent yield, it's wait what?
Oh, interesting. Why did we not use the 82.5? Because if I'd used 82.5, I would have gotten less than 100%.
So are we trying to do that?
We choose between the 82.5 and the 58.7 not to make our number less than 100%. But we choose between those two because one is the limiting reagent. To make 82.5 grams of magnesium chloride, I need more hydrochloric acid than 45 grams. How do you know that? Okay, I will accept that as an answer. Before we do that, though, because it's going to require me to erase everything, Everybody okay with what's written up there? Okay. So we heard an interesting question. So let's go through and take a look at that. So why did we not use the 82.5 grams of magnesium chloride? And the answer I kind of offhandedly gave, okay, I didn't prove. So guess what we're going to do? Let's prove it. If I start with 82, or need to make 82.5 grams of magnesium chloride, okay, that's what I got to make. Okay. I want to know how much hydrochloric acid I need to add to get that, which means my answer needs to be in what units? Grams hydrochloric acid. So I'm doing a new conversion. Okay. We're going to take 82.5 grams of magnesium chloride, so you said, okay. I want to convert that into grams of hydrochloric acid. Okay. So everybody on this side of the classroom, that's what you need to solve. I want you to convert 82.5 grams of magnesium chloride into grams of HCl. Okay. How did we get the 82.5? That came from this number, because Naya said, I don't understand why we didn't use that. Okay, so we're going to look at why we didn't use that after we solve this question. So take the 82.5. And for those of you panicking on this side, well, what does the other side of the classroom do? Okay, other side of the classroom, you get your own question. I want you to take 50.6 grams, no, of magnesium hydroxide. That's what we started with, right? 50.6 grams magnesium hydroxide. And what do I want you to convert that into? Grams of hydrochloric acid. Try it. Try it. That's not a bad idea. I don't know if she'll do it. Okay. So there we go. 2 questions. 2 questions I want you to go through. So are we ready for the big reveal? It's super exciting. Okay. Because this could be really confusing and loud, okay, we're going to simplify the number down to make it a little bit easier for me to interpret. I only want the number found in the tens place and the ones place. Right? Everybody okay with that? So, no decimals, just the first 2 numbers. Okay? We're going to do this as teamwork, because I noticed that people on both sides of the classroom have got this figured out. So you can yell at the other side of the classroom what your answer is. We ready for this? On 3, 2, 1. Okay, I don't know where you got the 71, but I heard 31, so you did a calculation mistake. 63 on the right, and what do we get on the left? 63. What the heck? They're the exact same answer. Why? It's the exact same thing. It's all related to the exact same equation, sourced using the exact same numbers. How did we get 82.5? By converting 50.6. So 82.5 and 50.6 are effectively one and the same through that conversion that we did Tuesday. Which means if I take 82.5 and convert that to something else, I'm going to get the exact same answer if I take the 50.6 and convert it to that same something else. Okay? So, back to the original question. Either way we solve this, we got how many grams of hydrochloric acid necessary? 63 grams of hydrochloric acid are necessary to do what? 63 grams of hydrochloric acid are necessary to make 82.5 grams of magnesium chloride. 63 grams of hydrochloric acid are necessary to react with 50.6 grams of magnesium hydroxide. Back to Naya's question. To react the 50.6 grams to make our 82.5, how much hydrochloric acid do we need to have? 63 grams. How much hydrochloric acid do I actually have? 45 grams of hydrochloric acid. This is why we can't use the 82.5 grams as our theoretical yield because I can't make that with only 45 grams of hydrochloric acid. I need 63. So when we did the comparison between those numbers and picked the smaller of them, it's because I can't possibly make the 82 because I don't have enough hydrochloric acid.
So should we test them the way you have to?
So deciding how to approach your limiting reagent question, do you want to go back and test them? Will that confirm that you are correct? Yes. Will it also add 10 minutes to your calculations? Yes. How much time do you have on the exam? If you've got a bunch of extra time because you whipped through everything else, fine, go ahead, check it. If you don't need to check it. Run off the standards that we've been working with. The smaller of those two numbers is our limiting reagent, which is our theoretical yield of our product, yes. All of the time. Okay? So the big lesson here, can we get an answer that is over 100% yield?
Yes.
Yes. Which means we have to ensure that when we calculate our percent yield, that we are plugging in actual and theoretical into the proper spaces. If we do not insert them correctly into our calculation, we will get a different number, and that different number will absolutely be an answer choice on the exam. Does that make sense? Okay. And with that, if I was wearing a hat, I'd say hats off to you guys. You did a really good job with that question. Okay. Primarily because I don't actually ask students to solve that question. But you guys did it. And you did it pretty well. So, good on you. Which takes us to all of our individual steps, and then into our last concept of this unit. Empirical formulas. Believe it or not, we've been working with empirical formulas already, because most of the compounds we've worked with happen to be ionic compounds. And when we look at an ionic compound, say sodium chloride, what is its formula? NaCl. Or a formula like magnesium chloride, what is its formula? MgCl2, right? Okay. Well, our empirical formula is the fully reduced whole number ratio of the elements within a compound. Right? So what is that saying? Saying that when we look at the formula for sodium chloride, it is not written Na2Cl2. Why not? Because I can reduce that to just ones. It is not written Na20 chloride 20. Because I can reduce it lower. If we looked at our magnesium chloride, it's not written as Mg200Cl400 because it's not a reduced ratio. Okay? So in our ionic compounds, we're always working with our reduced ratios. That's the whole point of them. It makes it easier to work with. Okay? But what happens if we move up to, say, a different compound, like a molecular compound? Say benzene. Did I cheat on this? Dang it. Okay. And because we've all taken lots of organic chemistry, we know exactly what benzene looks like. Awful lot of plurals in there. Right? We all knew that. Okay. Way to just accept that. Now you accept that, that means I got to test you on it. Oh. Okay. You aren't responsible for recognizing how to build compounds. Okay. That is something that is in a more advanced class, say, like organic chemistry. So if we looked at benzene, okay, we're less concerned about the structure, which is stupid. Okay? But in a general chemistry class, we don't care about the structure. We want to look at the formula. Because when we look at the formula, we don't see all these lines and stuff, and that causes us to panic and freak out. So give me the formula for benzene. Okay, well, is carbon there? So it'll be C, Well, how many carbons are there?
6.
I see 6. How many hydrogens are there?
6.
So that's the formula for benzene. But interesting, I keep hearing CH. What do you mean CH? I didn't ask for the empirical formula, I just asked for the formula. If we ask for the empirical formula, it becomes CH. Okay. Does that change my interpretation of the formula? If I look at the empirical formula for benzene, I see 1 carbon, 1 hydrogen. The structure that I might come up with might be something along these lines. Well, that's a problem because carbon's supposed to have 4 bonds, but it can't be bonded to anything else because there's nothing else in the formula. Okay? That's a pretty big interpretation issue. Okay? So when we're in our molecular compounds, okay, we typically want to use the molecular formula. And that's why we'll see it written out, even though we could reduce that down. How do we know this is a molecular compound and not an ionic compound? Because is a good place to start. What was that? They're both nonmetals. Our ionic compounds must have a metal and a nonmetal. Okay, because they're all nonmetals, this is a molecular compound, I'm okay with the formula C6H6. Okay? Unfortunately, the part that now comes into this is we have to be able to calculate and determine both our empirical formula and the molecular formula, given, of course, a bunch of mathematical numbers to interpret out of this. But before we jump into that, I want to draw your attention to one more thing. What are the meanings of the 6's, or the 6 in C6H6? What's that meaning of that first 6? The amount of atoms. There are 6 carbon atoms. And the 6, which I'll now call the blue 6, means 6 hydrogen atoms. Okay. If I wanted to weigh out benzene as a compound, okay, what would I use as the unit for that mass? The unit for mass is grams. Okay, there we go. We'd use grams. What is the mass in grams of 6 carbon atoms? In grams. I'm hearing 72 grams. Not true. It is negligible. Remember, the mass of a proton is 1.61 times 10 to the minus 24th kilograms. If I take 6 of those, fine. That's now 8 times 10 to the minus 24th grams. Or kilograms, whatever that unit is. That is stupidly small. I can't measure that. So what did we do to get it up to a reasonable measurable value? We introduced, and instead of looking at the number of atoms, which we said was a load of nonsense because I can't measure the number of atoms, I stopped looking at very small numbers of atoms and I look at very large numbers of atoms. And I create a new unit system that allows me to simplify that very large number into something very simple. And as Megan suggested, that is moles. That 6 does mean 6 atoms. It also means 6 moles. Which then means our 6 hydrogen atoms would necessarily become 6 hydrogen moles, or moles of hydrogen. So the numerical value in our formula represents the number of atoms. It also represents the number of moles. Which unit do we prefer to use? It depends on the context of our question. Okay. In everyday chemistry, which unit is more reasonable to work with? Moles, because that scales up our system into a function that we can then mass and weigh. If we aren't in that proper mass system, it becomes virtually impossible to do any experiment. Kind of make sense? Okay. So, This is a fun slide. Big summary of all the stuff we need to do. Okay. Number one, we've got our calculation for determining the empirical formula. We'll need to convert the units of whatever we're given into moles of each and every single one of the elements. Okay. Typically, you're given units of either grams, mass, which means we can convert the grams into moles using
The
periodic table, which is our, molar mass. Okay. The other times you're given a percent composition. Okay. The percent composition tends to freak students out because we don't know how to convert a percent into moles. Okay. What does percent mean?
per 100.
Per 100. Okay. What if I have 100 grams? I then take whatever my percent is, and it is now the number of grams of that substance. If I have the grams, then what can I do? Go back to step A, convert grams to moles. Once I'm in units of moles for each and every single one of my elements, I'm then going to divide all of the mole amounts by the smallest mole. Okay. What does that mean I'm going to do? If I had MgCl2, Mg200 Cl400. So the moles I got was 200 moles of magnesium and 200 or 400 moles of chloride. Step 2 says divide them both by 200, and what do I get? MgCl2. Holy crap, that's exactly what it's telling us to do. This is stuff that we're doing by inspection already. We can then insert that whole number into our formula, and we now have our empirical formula. The trickier one is our molecular formula. We will determine the molar mass of our empirical formula. Okay? So in the case of, this is a bit misleading, but if our case of benzene, we had CH. What would the molar mass of that formula be? Where do I find the molar mass? Yes, I like looking at the periodic table. It would be 12 plus 1. It would be 13 grams and 1 mole for the empirical formula. What I will then do is take the molecular molar mass. So the molar mass of whatever the molecule was. Okay? So I could look up the molar mass of benzene. The molar mass of benzene happens to be 72 grams per mole, assuming I didn't screw up the math there.
No, that's just the carbon by itself. You haven't added the hydrogen in yet. Yes,
Yes.
78.
Yeah, feel free to laugh. Thank you. I appreciate that.
It's an honest mistake. There's no need to
Doing it in my head, give me a break. 78 grams per mole is now the molar mass. So what I want to do is take that 78 and divide it by the empirical mass. So what's 78 divided by 13? What was that, Obed?
I think it's like 6.
I think it's like 6 point maybe 0.1, 6.02. Or actually I believe it's exactly 6. Okay. I will multiply the empirical whole numbers by whatever the number was that came out of 2. What was my empirical whole number for carbon? 1. What was the number that came out of 2? 6. So my molecular formula is C6H6. What was the formula for benzene? C6H6. Okay. So that's an awful kind of process because we're just looking at steps. So let's put it all together and actually solve it. An unknown compound of radium oxide is found to contain 0.726 moles of radium and 12.3 grams. Har. I don't know what you're talking about. That absolutely says of oxygen. What is the empirical formula? Okay. So what are we combining here? What are we looking at? We've got radium, Ra, and oxygen, O. What are the moles of radium? Oh, and remember our formula, right? We're trying to solve for the x and y in our formula. Need to be in units of moles. So radium, x is 0.726 moles. Perfect. What was y? Really creative. 1, 2, 3. Grams of, listed as oxygen atoms, so our symbol is O. To insert into our formula, what unit do I need to have? Moles. Our 12.3 grams of oxygen moles? What do I need to do? Convert it into moles of oxygen. How do we do that? Where do I find the relationship between the grams and moles of oxygen? Periodic table. 1 mole is 16 grams. I can punch that into the calculator, and what do I get as an answer? Did I cheat and put it up there? No, I didn't. Dang it. 0.768. Oh, 0.768 was kind of funny because I thought it was in sequence, but it's not. Okay. So my formula for radium is really just Ra 0.7260 0.768. Right? That's how we want to look at a formula, right? What do we want in our formula? Whole numbers. So what do we need to do? No. Divide by the smallest number. So we'll divide everything by the 0.726, and I end up with x equaling 1, and I would get y equaling very close to 1 and change, right? Like 1 point, maybe 1. So the formula I get is radium 1, oxygen 1, also known as, thank you, that's where I was going with it too. Rao. I now have my empirical formula. That's the calculation I have to work with.
So if it's like about 1, you just...
So as far as this class goes, every question that I will ever assign, those numbers come out darn close to spot on perfect.
Because on the... I don't know if it was on the practice form or in the...
It might have been in the homework. I might have screwed up on the homework and didn't calculate it. One of the kind of oddities that might show up is you might come up with, instead of it being 1, 1.5. Well, you're now off by exactly a half. So what can you do? It's 1.5. It's exactly in the middle. Double everything. What happens when we double everything? You become 3 instead of 1.5, and everything balances out. Okay? Which is kind of irritating, but that's the way it works. We could go through and look at our grams. You guys want to do that calculation?
Yeah.
Okay. Go ahead and do that calculation on your own. Okay. Oh, is there? No. Hopefully what you got as a final answer would be come up with the wildly creative and interesting answer of CH. Wow. Way to go, Mike, for being super creative. Okay. CH. There was 1 carbon, 1 mole of carbon, 1 mole of hydrogen in the empirical formula, our reduced ratio. Okay. So this you can do, so let's make it more difficult. Okay. Well, here, oh, that's the same question. Well, that's kind of dumb. Let's ask a different question. Okay, a small amount of the same sample, so the exact sample you just tested. That same sample was tested using a mass spectrometer, okay, which is a fancy way of determining the molar mass for that molecule. Okay. So that mass spectrometer tells us that the molecular mass of the compound itself is 78 grams per mole. What is the compound's molecular formula? So we've got our work written up there for most of it. We have to carry over our empirical formula from the previous question, which we solved to be CH. We need to determine the empirical mass. Well, the empirical mass is going to be the mass of carbon plus the mass of hydrogen. Okay? Do I want multiple carbons or multiple hydrogens in that sum? Why not? Because in the empirical formula, there's only one of each. I add those together by using the periodic table. You can see I got lazy and stopped using units. 12 plus 1 gets me our 13. So the empirical mass for our formula is 13. The next step, take the molar mass, our molecule's mass, divide it by the empirical mass. We get 6. What does that mean? The molecule is 6 times larger than the empirical formula. So how do I make it 6 times larger? There's an interesting idea. I could put parentheses around it and I could do that. Absolutely fair game. Or and again, great on Mike for being super creative. And we have the molecular formula for benzene yet again. Okay? You're responsible for being able to determine the molecular formula. You're responsible for determining the empirical formula. Questions about that? Okay, with the amount of time we've got left, there's a summary of your empirical and molecular formula steps. Okay? You might be able to tell I'm not a big fan of dealing with these because it involves a bunch of numbers, and we have a lot better techniques these days than trying to do a whole bunch of calculations. We can stick our compound into a machine, and the machine will spit out an answer. Okay? But you're responsible for being able to do it, at least theoretically, say the machine breaks. Okay? I do appreciate the pictures, because it makes me feel like I did a really good job making something. Oh my God.
They're going to be on my Snapchat.
Only if you put it on Twitter and say hashtag.
I feel really happy that you're taking pictures of everything.
Oh, that's sad.
But these slides are on Canvas. You already have access to them. And with that, we've got 10 minutes left. So we can talk briefly about review. But before we get into that, take no more than 5 minutes. I want you to write a reflection on this unit. What is the new content areas, or what are the new content areas that you are responsible for? What areas are you having troubles with? What areas do you feel super confident with? And then in particular, do you have specific questions? Okay. Mole of objects being that number, is that our periodic table now tells us the number of grams per mole of an element. That's the biggest thing to get out of that section. Okay? That our periodic table now gives us a mass-mole ratio. That's huge. Okay? So you will likely see that mass-mole ratio lots more times. The 6.02 times 10 to the 23rd, kind of limited. You're still responsible for it, but the numbers of calculations you do with that tend to be relatively straightforward and, quite frankly, boring. Okay? Largely because it involves powers of 10, and nobody likes dealing with that. Okay? After that, we looked at balanced equations. The power of the balanced equation gave you another conversion factor. It allowed you to convert from one substance to another. I can go from A to B as long as I know the relationship of A and B through a balanced equation. Okay? That's really powerful to be able to convert. Okay? The next thing we looked at was molarity. Okay? Within molarity, we had moles equaling liters, okay, for a solution. Okay? That is not something you would look up. That's something that's given to you. Unfortunately, when we look at molarity, typically how is it written out?
Big M.
As a capital M, which means if you see, say, 0.500 capital M NaOH, some people might have picked that one up. What does that mean? You have 0.5 500 moles of sodium hydroxide in 1 liter of a sodium hydroxide solution. Okay. Those of you on Thursday may be going, I don't know why he's making a big deal about that. Okay. Wait 4 hours. Okay. Roughly lab, 3 hours.
They have lab in 3 hours? Yes, he does lab.
At the end of the 3 hours, yeah. The next concept was gases. The big deal that came out of gases was that 1 mole of any gas is 22.4 liters when at standard temperature and pressure. That is a conversion factor you're responsible for. I personally think it is dumb. PV equals nRT is really what you should be using, but you aren't really tested on PV equals nRT this semester. You're more tested on that mole to liter ratio. It will always work. PV equals nRT will always work for an ideal gas. The mole equal 22.4 liters does not always work.
So the test will only be handling ideal gases?
The next big concept is our limiting reactant or reagent, which involves using everything above. The next concept was our percent yield, which involves everything above. The last concept is our empirical formula or our molecular formula, which gets at the meaning of what a formula is that does allow us to convert between substances within that formula unit. But that's about it. I believe that covers all of the new content for this exam. That still requires that you know how to pull things from older parts. The dimensional analysis, you need to know your unit conversions, milli, liters, grams, all that fun stuff. Okay, so a lot of stuff is still summarized in this. Within that content, remember, when we looked at the limiting reagent and percent yields, both of those questions, and even a molarity example, involved nomenclature. Okay, so nomenclature still shows up in this exam. You are responsible for all of that content. This is as close to a practice final as you're probably going to get. Okay. At this point, we have covered 80 to 90% of the course. Okay. Which is kind of nice because that just means we only have a couple more weeks left to just talk about some random sundry stuff, and then we can move on. And we can all be happy with our Christmas breaks. Questions? PV equals nRT has the gas constant R. You do not have to memorize that. That should be on the exam front already. If it's not, I will put it there. If it's still not, I'll write it on the board. Okay, looks like you don't have any other questions. So, unfortunately, we can't even get into the fun stuff of coming up with processes. So.